So in this video, we're going to look at periodic table trends, and specifically we're going to look at the trend of how radius changes in atoms as you go across the periodic table. So first, how do you even measure radius? Think about an atom. It's not just a simple Bohr-Rutherford diagram. It's actually this messy picture with a nucleus in the center and these orbital clouds that we find by solving Schrodinger's equation that tell us the probability of where an electron might be. It's a really messy, fuzzy picture. So how do you talk about a radius of something with such fuzzy boundaries? Well, one way to do it is mathematically. You can solve Schrodinger's equation for each atom and then look at the boundary where the electron is most of the time, or 95% of the time. But that can be actually really hard to do mathematically. So more practically, you might want to measure the radius of an atom experimentally. And to do that, you just have to measure the distance between two atomic nuclei and then divide by 2. If these atomic nuclei are bonded together, then taking the distance between their nuclei and dividing by 2 will roughly give you a measure of radius of that atom. So how do we actually look at what factors impact atomic radii on the periodic table? Well, there's two main factors that impact atomic radii. The first one is simpler, and that's just the energy level, or the highest energy level that an atom has. As you increase in N, or increasing your energy level, then your electrons must be further from the nucleus simply because the shells get bigger and bigger. And so if I look at, here's period 1 here with hydrogen. If I look at my hydrogen atom, it has a single proton and it has a single electron in the very first N equals 1 energy shell right there, right? Now if I go to period 2, look at somebody in period 2, maybe lithium. Lithium has 3 protons and 3 electrons, so 2 electrons in the first energy level, and then the next one is in energy level 2. And every time you go down in the periods here to period 3 or period 4, what you're doing is you're adding another shell, you're adding another energy level. And of course, if you're adding another energy level, those electrons are getting further and further from the nucleus. That means you have a bigger radius. So that one's not too hard to see, but that as you go down in the periodic table here, we are adding energy levels, and so we're getting to a bigger atomic radii. The trickier one to look at, I think, is effective nuclear charge. So for effective nuclear charge, what you want to do is imagine that you are a single electron, and specifically you're the very last electron to be added to your atom, and think about what charge you would feel. That would be the effective nuclear charge. So let's look at lithium. Lithium has 3 protons in the center, and then 2 electrons in the first energy level. And now you are that last electron coming in. Think about what you would feel. So you'll feel a draw towards these positive charges in the center here, right? But then you'll feel these negative charges in your first N equals 1 orbital. Those 2 negative charges are going to repel you. So overall, you'll feel a positive 3 from the nucleus plus a negative 2 from those inner electrons. You'll feel something like an effective nuclear charge of positive 1. I say roughly, right, because it's fuzzy. These clouds are fuzzy. They don't fully shroud the nucleus. They don't totally cover it up, but they reduce the feeling of that positive charge that that last electron will experience. Let's look at an example here. So this has 5 protons in the center, so this is boron. Boron would then have 5 electrons. I've drawn 4 of them so far. We're going to look at how the very last one, the last 5th one, feels as it enters. So first it would feel a positive 5 charge from the nucleus, and then it'll feel a repulsive force between all those electrons that are in between this last electron and the nucleus. Any electrons that get in between here, those are going to repel this electron away from the nucleus, and that will cause the effective charge to be less than positive 5. And I say positive 5e here. The e that I'm referring to is the charge on a proton or the charge on an electron. Same number, just a different sign. Electron is negative, proton is positive, which is 1.6 times 10 to the negative 19 coulombs. That's E there, the charge on an electron or the charge on a proton. It's a little trickier than that though. And the trickier piece is that only the inner shells, only the electrons in those inner shells actually shield the nucleus. So here I've got carbon, 1, 2, 3, 4, 5, 6 protons in the center. It'll have 2 electrons on its inner shell. So this is the n equals 1 shell, 1 electron here on that shell, and 1 right here. On that outer shell, there's going to be a total of 4 electrons, including, we're really looking at this last electron to be added, right? But a total of 4 on that outer shell. But these other 3, they're not really shielding the nucleus, so they're not going to have a big impact on Z effective. It's the inner 2 that will impact Z effective. So this carbon nucleus has a positive 6 charge, the inner electrons here, negative 2, and so overall this electron will feel something like a 6 plus negative 2, which is an overall positive 4 Z effective there. So what does that mean for our periodic table? Well, what it means is as you go to the right in the periodic table, you're going to be adding more and more protons to the center. So let's go from carbon here to nitrogen. We're going to add another proton in the center. So now the center is going to be positive. So this is carbon, sorry, that I drew before. That's carbon. Let's do nitrogen next. So nitrogen has a positive 7 charge in the middle, right? So that nucleus has a positive 7 charge, 7 protons in the nucleus. There's still 2 electrons in that first energy level. So there's still going to be roughly a negative 2 charge shielding the nucleus. But that leaves you with a positive 5 charge. So the effective nuclear charge of nitrogen is bigger than the effective nuclear charge of carbon. And that's true anytime you go within a period. So if you pick a single period, like period 4 here, as you go across from potassium to calcium, you're increasing the number of protons in the center, increasing the atomic number, without actually shielding the nucleus more, because the extra electrons you're putting in are getting thrown in the valence shell, so they're not shielding the nucleus. And so you're increasing your atomic number, your effective nuclear charge is going to be increasing as you go to the right in the periodic table within any given energy level or within any given period. So I know effective nuclear charge is a little bit tricky to understand. I'll try and make sense of it with a little bit of a metaphor. In our metaphor, we're going to use Kit Kat bars as protons because they're clearly a positive thing. So these are positively charged, and we've got we're going to start with lithium. Lithium has 3 protons in the nucleus, so I'll put in 3 Kit Kat bars in my nucleus. And then I'm going to use apples to represent electrons. Lithium has 2 electrons in its inner shell. That's n equals 1. And then it has 1 electron, the 3rd electron, in its outer shell. So if we're thinking about effective nuclear charge, we need a little bit of false nutrition information here. And this is something I like to imagine. I imagine that when I eat a Kit Kat bar, all of its unhealthiness can be canceled out if only I also eat an apple. So we're going to use that to imagine that apples and Kit Kat bars cancel each other out. Of course, that's not true from a nutritional perspective, but that's what we'll imagine. So if I look at this atom from the perspective of this outer electron, the apple in the outer shell, this electron sees 2 inner electrons and it sees this nucleus. So the nucleus is positive 3, the 2 inner electrons are negative 2, and so what this electron sees roughly is positive 3 plus negative 2, or basically an overall positive 1 charge here. Now if I move across the periodic table to the right, and I'm going over to beryllium, beryllium has 4 protons in the center, a charge of positive 4 in the center, and it has 2 electrons in that first shell and 2 electrons in the outer shell. So now we're still going to look at this whole atom from the perspective of one of those outer shell electrons. Now this electron doesn't necessarily notice another electron in its same shell because that's not like inside of it. From where it's at, the only things that are closer to the nucleus than this electron itself are these 2 electrons and the nucleus. But now the nucleus has 4 Kit Kat bars, or 4 positive charges in the middle, and in that n equals 1 shell, the inner shell, we've got 2 electrons. So what this outer electron is seeing is basically like a 4 positive charges minus 2, taking away 2 negative charges, leaving it with what looks like roughly a positive 2 charge. So this atom, beryllium, now has an effective charge of around positive 2. Now we move over to boron. So boron has an atomic number of 5, or 5 protons in the nucleus, 2 electrons in that n equals 1 shell, and now it's going to have 3 electrons in the second energy level. So looking at it from the perspective of one of these outer electrons, it now looks like we've got an inner nucleus with a positive 5 charge, and there's only 2 electrons that are kind of taking away from that on the inside. So that brings the charge down to 3, positive 3. And these electrons here, they're all in the same level as our outer electron here. So they're not really going to shroud the nucleus or cover up that positive charge or cancel it out the way that those inner apples or inner electrons would do. So this now looks like it has an effective nuclear charge of 3. So as you can see, or around 3. So as you can see, as you're going towards the right on the periodic table, every time we move over an atom to the right, we're increasing our effective nuclear charge. So pulling that all together, as your effective nuclear charge decreases, and that happens as we go to the left in our periodic table here. So as we're going to the left within a period, our effective nuclear charge will decrease. That means that the electrons will be held more loosely. So those outer electrons, right, the effective nuclear charge is, well, what charge do they feel? And if they feel a really big positive charge from the center, then they'll be held more tightly. That makes the atom smaller, a smaller radius. But if they feel a kind of a lower Z effective, less of a positive charge from the nucleus, maybe because it's really shrouded by those inner electrons, then the radius is going to increase because those electrons will be held more loosely. So as you go to the left in a period, your effective nuclear charge goes down, the electrons are held a little bit more loosely, and the radius of those atoms increases as you go to the left. The other one is more straightforward. As you go down in the periodic table, you're increasing the energy level, right? We go from period 1 to period 2 to period 3. Each time we go down and in the periodic table for a row or a period, we're going up in the number of energy levels that the atom has. That means we're starting with our nucleus, right? And then we're adding, that's a nucleus. We've got the first energy level in there's a Bohr-Rutherford version, but it's kind of the same idea with quantum 2. Then we have another energy level. That's just bigger, right? A third energy level. If you get up to n equals 3 here, it's going to be even bigger. So that makes sense that as you go down in the periodic table, you're going to increase in radius because you're adding more energy levels. So drawing those two trends on one periodic table, as you go down in the periodic table, radius will increase because the number of energy levels you have increases, n increases. And as you go left in the periodic table, the radius will increase because each atom is holding those outer electrons more loosely because their effective nuclear charge is going down, Z effective is going down.